I'm Chen Fengye from the Hong Kong University of Science and Technology, and today I'm here on behalf of these authors, to present their work of the choreograph construction as they cannot attend here today. First, we go through the background of the choreograph. The choreograph encodes the caller-to-callee relations among the functions. This is fundamental to understanding the program. For example, here is a code example in the corresponding choreograph from which we have two core edges from the main function to the callee functions. Choreograph construction is also one of the most fundamental tests for the programming analysis and the verification that has been studied over the years. When we search for the keyword that the choreograph, we can find over 5 million hits on the Google Scholar. And the back to its history, in the 1979, that Barbara Ryder, the pioneer of the programming language research, published the first algorithm for constructing the choreograph for the Fortran programs. And in terms of the C language, it still powers the world today. That many fundamental systems and software are still written by the C language. In the C programs, the choreograph and the indirect call use the function pointer to invoke the functions. This includes the benefit of it can enable more compact code, and it can enable the dynamic behavior in the language. And according to our study of file representative open source softwares on the GitHub, we can find that over 16% of the functions, they are just taken functions that call by the indirect calls. And here is a simple example to illustrate that the choreograph in indirect call in the C function, that the address of the subtract function is assigned to the function pointer at the line 5, and then it will invoke at the line 6 through the function pointer fp. However, despite the convenience of using the function pointer, that the function resolving the indirect calls in the C language is very challenging problems, and all the existing ones, they either suffer from the low precision or the low efficiency problems. For the type analysis, the type analysis checks the type compatibility between all the just taken functions and all the function pointer to resolve the indirect call targets. But it overlooks the load and store memory operations. So as a result, that the type analysis is scalable and can analyze the 10 million lines of code in minutes, but it's very imprecise. Furthermore, for some function with the general type parameters such as void or void star types, it will match a larger of the unrelated functions, resulting in the low precision. Here is a further example that here there are two just taken functions, the subtract and the add. If we are using a type analysis, we will resolve that at the line 9, the function pointer will call into both of them. Because the type of the function pointer match the type of this just taken function, but actually only the subtract is the valid calling target of the indirect call function pointer. On the other hand, the pointer analysis is inefficient. The pointer analysis is precise by computing the possible values of each function pointer with the consideration of the memory load and store operation. For example, here the pointer analysis can reason that at the line 9, the FP responds to a address of the subtract, so that this indirect call will call into that function. However, in practice, the pointer analysis must account for many complicated conditions such as the complex control flow, multiple calling context, and memory load and store operations. And these factors will result in the inefficiency of the pointer analysis. The goal of this work is to improve the traditional type analysis, which can scale up to million lines of code, but is still imprecise. The key insight is that in the program, there are many simple function pointers. They neither expose their address, or they divide their value through the pointer dereference. And this, for these function pointers, we can use the points to analysis to analyze the points to target in an efficient manner. And for the remaining function pointers, they are the complex function pointer, and they cannot be effectively resolved by the pointer analysis. And furthermore, we give the notion of the confined functions that they are the just taken functions that are only invoked by the simple indirect course. Here we give a concrete example that at the line 1, the function pointer B1 is a simple function pointer because it neither divides value through the memory indirection or they expose the address to the memory. But the B2 is a complex function pointer because at the line 3, it divides the value through the load operation. So consequently, at the line A and the line 9, these two indirect codes, they are simple indirect code and the complex indirect code respectively. And furthermore, the function QS, as our definition, is a combined functions because its value only propagate to the line A, which is a simple indirect code. So based on this notion and the characteristic of the function pointer, the key idea is to separate the simple indirect codes from the complex indirect codes. So specifically, we can use the points to analysis to resolve the simple indirect codes to embrace the high precision, and then use the type analysis to resolve the complex indirect codes to avoid the performance penalties. And furthermore, for the remaining complex indirect codes, as we mentioned that the conventional type analysis is, we still try to match them with all the just taken functions, and which is will result in the imprecision. So to address this problem, our idea is that the confined functions, they are only invoked in the simple indirect codes, thus cannot be invoked by the complex indirect code. So in this way, we can consider fewer just taken functions while we perform a type matching between the complex indirect codes to these just taken functions. So in conclusion, for both the simple indirect codes and the complex indirect codes, the approach can get improvement compared with the traditional type analysis. In this work, so it presents a Kelp which consists of two key stages. In the first stage, that is desire depth use analysis, that is the kind of pointer analysis to analyze to resolve the simple indirect codes. And in the second stage, it first excludes the confined functions. They are only invoked by the simple indirect codes, so that only the remaining functions will be type matched with the remaining complex indirect codes. We give a concrete example here. The function QS is actually valid indirect code targets at the line A through the function pointer B1. And the function BAZ is valid indirect code target of the B2 at the line 9. If we are solely using a traditional type analysis, both of these two functions will be regarded as the valid calling targets of these two function pointers due to the type match of them is valid. So in the Kelp, how do we do it? We first traverse the depth U-chain of the function pointer B1, and then we will finally reach the statement 1 which is just assignment that address of the QS is assigned to the B1 pointer, and this means that the indirect call at the line 9 at the line A will only call into this QS function. So in this way, the function pointer B1 is precisely resolved. For the remaining function pointer B2, we also traverse its depth U-chain. And in this case, that at the line 3, we will reach load installment. So this means that this function pointer is a complex function pointer. It will be left to the second stage. In the second stage, it will first recognize that the QS is a combined function whose address is only propagated to the simple indirect code side at the line A, so that the type analysis will only try to match the pointer B2 to the function remaining functions that the BAZ. So in this way, our approach can precisely compute that each calling target per indirect code. In terms of the evaluation, it led 20 real projects that and the large software systems that following the existing program analysis work. And these projects are large and difficult to be analyzed by the precise pointer analysis in a few minutes. In terms of the baseline, we choose the multi-layer type analysis, which is also the best paper of the CCS 2019. We evaluate the choreograph construction with the 3 metrics. In terms of the precision, we measure it by the average callee size of each indirect call. And for the performance, we measure it by the time consumption. We also measure the recall by checking whether there are any false negatives. It also performed the downstream application analysis to check whether the constructing choreograph can effectively assist with the several applications, including static concurrency analysis, the static bug finding, and the dynamic grable fuzzing. The result shows that in terms of the precision, it can reduce average callee target by 55% compared with the existing work and introduce no false negatives. And it also only incurs 7% of the time overhead compared with the existing work. For example, while analyzing the Linux kernel with 27 million lines of code, we can finish the analysis with 11 minutes and with 1 GB peak memory. And in terms of the downstream application, the result shows that the choreograph can significantly improve this application while only incurring a few seconds in the time overhead. And we also give further distribution of the simple function pointer and the confine function here. If you want to know more about the details about the evaluation and the technique, please feel free to refer to the paper. That's all of the presentation. Thank you.